predicting outcomes in highly complex, multidimensional environments requires a precise mathematical architecture. The strict objective of a regression model is to map a d-dimensional input space, our feature matrix X, to a continuous, real-valued target vector, Y. The continuous nature of these labels is the single defining characteristic that separates regression from classification. We are calculating specific, infinite-resolution magnitudes, not sorting data into discrete, finite categories. Because of its ubiquity, linear regression is frequently treated as a solved elementary algorithm, a trivial stepping stone to bypass on the way to deep learning. This is a miscalculation. Linear regression is an elegant mathematical equilibrium, where three entirely distinct fields of mathematics intersect to solve the exact same problem. Those fields are calculus, treating the model as an optimization problem, linear algebra, treating it as spatial geometry, and statistics, which treats it as probability. Tracing how these three independent frameworks arrive at the exact same algorithmic conclusion provides the structural mechanics required to understand advanced nonlinear machine learning. Mastering this algorithm establishes the foundational mechanics for every subsequent architecture, from kernel methods to deep neural networks. We will begin with the calculus framework. The basic mathematical structure of a linear model is a weight vector, W, transposed and multiplied by a feature vector, X. To measure the accuracy of these weights against our true labels, we use a loss function called the sum of squared errors. The equation includes a 1/2 multiplier at the front, included strictly for mathematical convenience to cancel out the exponent during derivation. This shows the sum of squared errors. Plotted across two weights, it forts a continuous 3D topographic grid resembling a bowl. Its defining geometric property is strict convexity, providing a critical guarantee. Any local minimum is definitively the global minimum. There are no false bottoms. To find the lowest point, we calculate the gradient. Computing this is expensive, so stochastic gradient descent prioritizes speed. By extracting a random subset, it approximates the gradient. This erratic path downward perfectly converges at the global minimum due to strict convexity. The optimization lens provides a mechanical engine for finding optimal weights. However, it treats data purely as an abstract mathematical landscape to traverse, completely ignoring the internal relationships between the features themselves. If we abandon calculus entirely, we can rederive the exact same model using the spatial logic of linear algebra. Here, the data matrix X is not a loss landscape. It is a collection of distinct feature vectors spanning a specific, rigid subspace. This flat plane is the feature row space. Target vector Y points entirely outside it. Because predictions are trapped within the plane, perfect matches are impossible. We drop an orthogonal shadow from Y onto the plane. This perpendicular error vector is completely orthogonal to X. Expanding this zero-product orthogonality equation instantly yields the normal equations. The explicit solution requires isolating W, which we achieve by multiplying the target vector by the pseudo-inverse of the feature matrix. The calculus minimum we found earlier is visually identical to the geometric shadow of our target vector, projected against the limited dimensions of our data. The third framework discards spatial geometry and calculus entirely, examining the system strictly through statistics. Here, we operate on a core probabilistic assumption. The underlying linear relationship is correct, but true labels are corrupted by environmental noise. This single data point floats away from our prediction line. We map the statistical distribution of that error by applying a noise profile. Assuming zero mean Gaussian noise means most errors are small, and large errors are exponentially rare. Our objective is maximum likelihood estimation, or MLE. We need to find the specific parameter W that makes the observed dataset the most statistically probable outcome. We frame this mathematically using the likelihood equation, derived from the product of the Gaussian probability density functions. Taking the natural logarithm converts these heavy exponential products into a sum, leaving us with the log likelihood. Look closely at the core variable remaining. It's the exact same squared difference between the true label and prediction that we minimized in the calculus lens. Because the Gaussian exponent carries a negative sign, finding the maximum value of the overall probability function requires finding the minimum value of that squared difference. Minimizing squared error is mathematically optimal if and only if the universe corrupts our data with normally distributed noise. Optimization, geometry, probability. 3 independent frameworks operating on completely different rule sets, all independently deriving the exact same normal equations. This composite visualizes that mathematical consensus. The convex bowl, the orthogonal projection, and the maximum likelihood all condense into a single explicit matrix solution. Yet this consensus holds a critical limitation. It relies entirely on explicit, linear relationships within the raw feature space. Real-world data is rarely linear. To capture complex realities, we must transform our theta matrix X into a new matrix, phi of X, mapping our features into extremely high or even infinite dimensions. But this creates a computation trap. Calculating explicit weights for a vector that has infinite dimensions is mathematically impossible. Recall the normal equations, xx transpose w equals xy. Because the solution for w is derived from the product of our data and the target vector, the weight vector is mathematically constrained to lie within the span of our data points. This allows us to express w not as an independent vector, but as a linear combination of our observations, represented here as our transformed data, phi of x, multiplied by a coefficient vector, alpha. Notice that by using this representation, the transformed features only ever interact with each other via dot products. Because of this, we never actually need to explicitly calculate the infinite dimensional vectors. We replace the massive inner product entirely with a kernel matrix, K. This matrix bypasses the high-dimensional coordinates completely, instead computing a direct scalar value representing the similarity between any 2 data points. We are no longer calculating explicit feature weights. We are now optimizing alpha, a coefficient that determines the relative importance of each specific data point compared to the others in the dataset. By isolating the algebraic and geometric constraints of a simple linear function, we can map data into infinite dimensions without performing infinite calculations. Understanding linear regression yields the underlying architecture of advanced machine learning.